Let's take a look at the tangent function. Recall that the quotient identity for tangent x is equal to sine x over cosine x, which tells us that the tangent function will be undefined when the cosine x is equal to 0. Let's see when that happens. The cosine is equal to 0 when x is equal to 2n plus 1 over 2 times pi, which is another way of saying odd multiples of pi over 2. So as you can see in my table, I know that this function is going to be undefined at pi over 2. Some other values, remember it's odd multiples of pi over 2, so that would be 3 pi over 2, 5 pi over 2, negative pi over 2, and so on. Next, the tangent function will be equal to 0, or the x-intercepts, when the sine function is equal to 0. Let's see when that happens. Well, the sine is equal to 0 when x is equal to n times pi. And again, in both of these cases, n is any integer. So that means that the zeros or x-intercepts will occur at 0, pi, 2 pi, negative pi, and so on. So you can see in my table I've got the value of 0, 0. So now I've listed some values for tangent function. The first 4, you should know these are special values. So and I've plotted those points on my graph. What we want to see is that when we choose x values closer and closer to pi over 2, the values of the tangent function increase without bound, which means that there's a vertical asymptote at pi over 2. So let's put that on our graph. And so we know that this graph from 0 to pi over 2 looks like this. Now, tangent function happens to be odd. Let's see why. If I look at the tangent of negative x, using the quotient identity again, that's going to be the sine of negative x over the cosine of negative x. And you need to recall that, remember, the sine function is odd, which means the sine of negative x is negative sine x. Cosine function, remember, is even, which means the cosine of negative x is the same as the cosine of x. And I can see that that's going to equal negative tangent x. So we know the tangent function is odd. What does that mean? It means that the graph is symmetric about the origin. So we can get another piece of the graph. So remember, it's undefined at negative pi over 2. And if I reflect this part about the origin, the graph looks like this. So here's one cycle or period for the tangent graph between negative pi over 2 and pi over 2. We call this cycle the principal cycle. And there's a couple of key special points that you need to know for this graph. Let's draw those points right now. So at pi over 2 and negative pi over 2, the tangent function is undefined. It's 0. The origin is one of the special points. The point pi over 4, 1, is an important point, as well as negative pi over 4, negative 1. So this graph you should know very well. It shows where the asymptotes are. It shows these 3 points. We call this the center point. It's obviously in the center of the cycle. These 2 points, we call them halfway points. And of course, this is another halfway point. And this, of course, is the center point. So you need to know negative pi over 4, negative 1, 0, 0, pi over 4, 1 for the tangent function and the asymptotes at negative pi over 2 and pi over 2. So now that we know that what one cycle looks like, let's look at some more cycles and come up with some characteristics for the tangent function. Here I've drawn 3 cycles for the tangent function, and we want to look at some of the characteristics of the graph. The first thing we want to observe is what the domain is. The domain is all real numbers x such that x cannot equal 2n plus 1 over 2 times pi, where n is any integer. Again, that's saying all odd multiples of pi over 2. It's undefined, so that's the domain. So you can see at pi over 2, 3 pi over 2, those are values that are not in the domain. The range of the function, look at the y values, is negative infinity to infinity. The period, here we have 3 periods. Here's another one. Period is pi. And the principal cycle we will call from negative pi over 2 to pi over 2. So these are very important concepts that you need to know about the tangent function. Let's look at some more. The tangent function, remember, is undefined. And where it's undefined, there are vertical asymptotes. They occur where x is equal to 2n plus 1 over 2 times pi. Again, odd multiples of pi over 2. Look at the graph. Have a vertical asymptote of pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. The next one would be at 5 pi over 2. The y-intercept, we can see, is at the origin. The y-intercept is 0. For each cycle, there are 3 important points. One of them is called the center point. So on these periods, I can see I have a center point at 0, 0, center point at pi 0, center point at negative pi 0. The x-coordinates of those center point, the x-intercepts or the zeros, are of the form n pi, again, where n is any integer. So again, 0, pi, negative pi, 2 pi. And the y-coordinate of all those center points is 0. Next, we have halfway points. For each cycle, there are 2 halfway points. The halfway point to the left of the center point is located midway between the x-coordinate of the left vertical asymptote and the x-coordinate of the center point, and the y-coordinate of that center point to the left is negative 1. The halfway point to the right of the center point is located midway between the x-coordinate of the center point and the x-coordinate of the right vertical asymptote, and the y-coordinate of those halfway points is 1. Next, we see that the tangent function is odd. That means the graph is symmetric about the origin. And lastly, the graph of each cycle we can see is 1 to 1. Remember your horizontal line test. If I look at one cycle, it passes the horizontal line test. So each cycle is 1 to 1. You need to be very familiar with these characteristics and be able to graph one period for the tangent function. Let's take a look at sketching functions of the form y equal a tan bx minus c. Recall that the principal cycle for y equal tangent x was negative pi over 2 to pi over 2. When you're sketching functions in this form, the principal cycle will occur when bx minus c is between negative pi over 2 and pi over 2. So in this example, we have y equal 2 tan x minus pi over 4, and we want to sketch this graph. So the first thing we're going to do is notice that b is positive. In this case, b is 1. C is pi over 4. If b is negative, you would have to rewrite it. Remember that the tangent function is odd to make the b positive, and then you would begin. So in this case, our b is positive. So we take our bx minus c, which in this case is x minus pi over 4, and we put it between negative pi over 2 to pi over 2 to determine the principal cycle for this function. So we want to solve for x, so we want to add pi over 4 to each side, so that would give me negative pi over 4 less than x. Pi over 2 plus pi over 4 would be 3 pi over 4. So here's what I know. I know the principal cycle for this function is going to be negative pi over 4 to 3 pi over 4. Notice that the period, the length of that interval, is still pi. You can always find the period by taking pi and dividing by b. Remember, the normal period for tangent is pi, and of course in this case b is 1. So we can see the period is pi. So now we know the principal cycle, we can figure out where the left and the right vertical asymptote occur for this principal cycle. The left vertical asymptote is going to be at x equal negative pi over 4, and the right vertical asymptote will occur when x is equal to 3 pi over 4. So let's go ahead and put that on our graph. So let's see, we have negative pi over 4 and 3 pi over 4, and I know those are where my vertical asymptotes are. Next, we need to find those 3 key points. Let's start with the center point. Recall that the center point is located, the x-coordinate is going to be located midway between the x-coordinate of the left vertical asymptote and the x-coordinate of the right vertical asymptote. So that means our x-coordinate will be, you can add up these coordinates and divide by 2, which gives me 2 pi over 4 divided by 2, which is pi over 4. So the x-coordinate of the center point is pi over 4. The y-coordinate of the center point is 0. So the point that I have now, my center point, let's write it up here, is pi over 4, 0. So let's go ahead and plot that point. Pi over 4, 0 is my center point. Next, we need to find the 2 halfway points. Let's find the halfway point to the left of this center point. To get the x-coordinate of the halfway point to the left, it's going to be located halfway between this left vertical asymptote and the x-coordinate of the center point. So the x-coordinate will be negative pi over 4 plus pi over 4. And again, you divide that by 2. Well, the numerator is 0. 0 divided by 2 is 0. The y-coordinate. Well, remember the y-coordinate for the normal tangent was going to be down at negative 1. So what you do to get the y-coordinate of this halfway point, you're going to multiply that y-coordinate of negative 1 for the basic tangent, and you're going to multiply it by a. Notice in this case my a is 2, so I'm going to do negative 1 times 2, which gives me negative 2. So this halfway point would be 0, negative 2. Now we need to find the halfway point to the right of the center point. Well, again, the x-coordinate will be located midway between this x-coordinate of the center point and the x-coordinate of the right vertical asymptote. So that's going to be pi over 4 plus 3 pi over 4. Again, divide by 2, so that gives you pi divided by 2 is going to be the x-coordinate of this halfway point. The y-coordinate is going to be, recall the y-coordinate to the right of the normal tangent, y equal tan x, is positive 1. So you're going to multiply that positive 1 times a, which in this case is 2. So the y-coordinate of this halfway point is going to be 2. So this point will be pi over 2, 2. So we'll plot that point. So I can see that this sketch, the graph will look like this. This is what this one cycle will look like for this particular tangent function. Very important that you remember how to find these points and how you find the principal cycle and the left and the right vertical asymptotes. Let's look at this example. We have y equal negative tan, parentheses 1/2 x plus pi, and we want to sketch this graph. The first thing we want to determine is the principal cycle. The principal cycle will occur when bx minus c, which in this case is 1/2 x plus pi, is between negative pi over 2, which recall is the negative pi over 2 to pi over 2 was the principal cycle for tangent. Now we want to solve this for x. So first I want to subtract pi. So let's see, now I need to multiply by 2. So now I know that the principal cycle for this function is negative 3 pi to negative pi. Now that I know the principal cycle, I know that the left vertical asymptote is x equals negative 3 pi, and the right vertical asymptote will be x equals negative pi. So again, to determine the principal cycle, you take the argument bx minus c, you put it between negative pi over 2 and pi over 2, you solve. That will give you the principal cycle. The left of the principal cycle tells you the left vertical asymptote, and at the right gives you the right vertical asymptote. Now let's find the 3 special points. Let's find the center point first. Well, recall the center point is located midway between the left and the right. The x-coordinate between the x-coordinate of the center point is located midway between the left and the right vertical asymptote. So, negative pi. So if I take negative 3 pi plus a negative pi divided by 2, that gives me negative 2 pi for the x-coordinate of the center point. And the y-coordinate of the center point is 0. So my center point, let's write, is negative 2 pi, comma 0. So let's go over to our graph and let's show what we have so far. Let's put in the left vertical asymptote. So let's say that's negative pi. Let's say this is negative 3 pi. So I know I have a vertical asymptote here and here. And I know the center point is negative 2 pi 0. Now we need to find the halfway points. Well, the halfway point to the left of the center point, the x-coordinate is located midway between this vertical asymptote and the x-coordinate of this center point. So that will be, the x-coordinate will be negative 3 pi plus a negative 2 pi, or negative 2 pi divided by 2. Well, that's negative 5 pi over 2 is the x-coordinate of this halfway point. The y-coordinate, we have to remember what the principal cycle for tan x. Remember, the halfway point to the left on y equal tan x, the y-coordinate to the left of the center point is negative 1. So we take that negative 1 value and multiply it by our a. Notice in this case, our a is negative 1. So we have a negative 1 times a negative 1, which of course is 1. So this halfway point is negative 5 pi over 2, comma, positive 1. So let's show that. Okay, now we have one more halfway point to find, the one, of course, to the right of the center point. Its x-coordinate is going to be located midway between the x-coordinate of the center point and this vertical asymptote, so that's going to be negative 2 pi plus a negative pi, or negative pi over 2. That's negative 3 pi over 2 is the x-coordinate of this halfway point. And the y-coordinate you find by taking the y-coordinate for the basic tan x, which is positive 1 times a. And again, a is negative 1, so the y-coordinate of this halfway point is negative 1. So this point would be negative 3 pi over 2, negative 1. Let's plot that point. Okay, so now we've got center point, our halfway points, our vertical asymptotes. So here is one cycle for this tangent function. Let's take a look at the cotangent function, y equal cotangent x. First thing I want to use is, remember, the cotangent function used in the quotient identity is the same thing as cosine x over sine x. So this means the cotangent function will be undefined when sine x is equal to 0 and when does that happen? That occurs when x is equal to n times pi, where n is an integer. So it's undefined, for example, it's 0, pi, 2 pi, negative pi. I've listed those in my table. The next thing is it's equal to 0, or the x-intercepts occur when cosine x is equal to 0. And that occurs when x is equal to 2n plus 1 over 2 times pi, or odd multiples of pi over 2. So at pi over 2 it's 0. The next one would be 3 pi over 2, 5 pi over 2, and so on. So I've got that point. Pi over 4 and 3 pi over 4, those are some special values you should know. The cotangent of pi over 4 is 1. The cotangent of 3 pi over 4 is negative 1. So I've plotted those 3 points. Where the cotangent function is undefined, that's where your vertical asymptotes will be. So there's one here on the y-axis, and there's one here at x equals pi. So the one cycle for this cotangent will look like this. We can see the length of that interval is pi. So the period is pi. And we call this cycle from 0 to pi, we call this the principal cycle for cotangent. You need to know where those asymptotes are. And then let's look at these points. There are 3 special points for the cotangent. We have the center point located at pi over 2, 0. We have a halfway point to the left of that, pi over 4, 1. And our other halfway point to the right of the center point is 3 pi over 4, negative 1. It's very important that you learn this graph, that you can draw one cycle, including the asymptotes and the 3 important points. Here I've drawn 3 cycles for the cotangent function, and we want to look at the characteristics of the cotangent function. The first is the domain. That's the values of x. X can be any real number except n pi, where n is any integer. So that means, for example, it's undefined at 0, pi, 2 pi, negative pi, and all multiples of pi. So that's the domain. Next, let's look at the range, the y values. Well, we can look at a cycle and we can see that the y values go from negative infinity to infinity. The period for the cotangent function we can see is pi. This is what we call the principal cycle. But we can see another period over here. And so you need to know that the period for cotangent is pi. And you need to know that the principal cycle for the cotangent function is 0 to pi. From here to here is the principal cycle. Now let's look at some other characteristics. Because it's undefined, there's vertical asymptotes at all values x equal n pi. So on this graph you can see I have a vertical asymptote at x equals 0, x equals pi, x equals 2 pi, and x equal negative pi. All multiples of pi there will be vertical asymptotes, and you need to know where they occur. We can see from the graph that there's no y-intercept since x cannot equal 0. Now for each cycle there are 3 special points, and you need to learn these points and be able to plot them. Let's talk about the center point first. The center point is located halfway between the left vertical asymptote and the right vertical asymptote. So the x-coordinate is right in the middle between the left and the right vertical asymptote. And the y-coordinate of the center point is 0. So all of these, you can see 3 center points. They always occur, the x-coordinate is midway between the left vertical asymptote and the right vertical asymptote, and the y-coordinate is always 0. Now let's look at the halfway points for each cycle. Let's look at the halfway point to the left of the center point. Let's look at this one. The x-coordinate of this halfway point is located midway between the left vertical asymptote and the x-coordinate of the center point, and the y-coordinate of that halfway point is 1. Next, let's look at the halfway point to the right of the center point. Let's look at this one. Its x-coordinate is located midway between the x-coordinate of the center point and the right vertical asymptote, and the y-coordinate of this halfway point is -1. So you need to know how to plot and find those halfway points and center points. Next, we can see that the graph of the cotangent is odd. I can see that the graph is symmetric about the origin. Remember, because it's odd, that means that the cotangent of -x is the opposite of the cotangent of x. And lastly, we can see that for each cycle for the cotangent function, that it passes the horizontal line test, which means that for each cycle, the cotangent function is 1-to-1 on each cycle. You need to learn all these characteristics of the cotangent function and be able to graph at least one period showing the asymptotes and showing the center point and the halfway points. Let's take a look at sketching functions of the form y = a cotangent bx minus c. In this example, we want to sketch the graph of 3 cotangent x plus pi over 3. When you have functions in this form, the first thing you want to note is if b is positive. If b is not positive, then you would rewrite this function using the fact that the cotangent is odd. In this case, I can see my b is 1, so we don't need to rewrite it. Recall that the cotangent function, the principal cycle for y = cotangent x, was between 0 and pi. So in order to find the principal cycle for functions in this form, we're going to let bx minus c, in this case x plus pi over 3, we're going to put it between 0 and pi, and this will give us the principal cycle for this function. Solving for x, subtracting the pi over 3, we can see that the principal cycle for this function is -pi over 3 to 2 pi over 3. Now the length of that interval would be the period, and the length of that period, that interval is pi. We can always find the period by taking pi, the normal period for cotangent x, and dividing by b. In this case, b of course is 1, so I can see that that's pi. Now that we have the principal cycle, we can find the left vertical asymptote and the right. The left vertical asymptote will occur when x is equal to -pi over 3, and the right vertical asymptote would be when x is equal to 2 pi over 3. Now we want to find the center point. Well, the center point is located midway between the left and the right vertical asymptote. Let's go ahead and put our asymptotes on the graph now. So we have -pi over 3. Let's see, if this is 2 pi over 3, then about right here. So I have an asymptote here, and I have an asymptote here. So the center point is located midway between the left and the right vertical asymptote. Let's find the x-coordinate. Well, I don't need a right coordinate. Let's just do x equals. So the x-coordinate will be -pi over 3 plus 2 pi over 3 divided by 2. So that's pi over 3 divided by 2 is pi over 6. And the y-coordinate of this center point is 0. So the center point is pi over 6, comma 0. So remember, it's midway between, so let's try to eyeball. That looks about right. So pi over 6, 0 is my center point. Now we need to find the halfway points. Well, let's find the halfway point to the left of the center point. The x-coordinate to the left of this center point is located midway between the left vertical asymptote and the x-coordinate of the center point. Well, let's see what we get. That's negative 2 pi over 6, so negative pi over 6 divided by 2 is negative pi over 12. Now we need to find the y-coordinate. Well, in order to find the y-coordinate, we have to recall, when you look at the graph of y equal cotangent x, the y-coordinate to the left has a y-coordinate of positive 1. So we want to take that y-coordinate of 1, and we want to multiply it by a. In this case, my a is 3. So I want to do 1 times 3, which of course is 3. So this halfway point is negative pi over 12, 3. So looks about right here, negative pi over 12. And we want to be up at 3. Now we need to find the halfway point to the right of the center point. Well, the x-coordinate, this halfway point is going to be located midway between the x-coordinate of the center point and the right vertical asymptote. So let's see what that gives us. Pi over 6 plus 2 pi over 3 is the same thing as 4 pi over 6. So I have pi over 6 plus 4 pi over 6 is 5 pi over 6. Well, that gives me 5 pi over 12 is the x-coordinate. And then to find the y-coordinate, we need to remember again the y-coordinate for the halfway point for the basic cotangent is negative 1. So we need to do negative 1 times our a. And again, my a is 3. So this will be negative 3. So this halfway point is 5 pi over 12, negative 3. And it's located halfway between there. So this would be 5 pi over 12. And then I need negative 3. So this is the sketch of this particular cotangent function. Once again, for cotangent, it's very important that you remember that your bx plus c has to be between 0 and pi because that's the principal cycle for the normal cotangent. Also, make sure you know how to find the center point and the halfway points. Let's take a look at the cosecant function. Recall that the cosecant function is the reciprocal of the sine function, so it's equal to 1 over the sine of x. In order to get the graph of the cosecant, what we're going to do is first look at the sine function and then use reciprocal identities. So let's do this first. Let's lightly sketch the sine function over here. You should remember the sine function very well. Its period is 2 pi. It's 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and then 2 pi back to 0. Of course, we can draw another period. Okay, so we've sketched the sine x, 2 periods for the sine x. If the cosecant, which it is, the reciprocal of the sine function, first of all, notice that the cosecant function is going to be undefined when the sine of x is 0. And the sine of x is equal to 0, we can see, when x is equal to n times pi, where n is an integer. Now, when the sine of x is 0, that's going to give you your vertical asymptote. So we know at all multiples of n pi, there's going to be vertical asymptotes. So I know there's going to be an asymptote here on the y-axis, here at pi, here at 2 pi, negative pi, and then negative 2 pi. Now, notice that the maximum point for a sine function is pi over 2, 1. The reciprocal of 1 is 1, so this point will also be a point on the cosecant function. Look at all these values for sine x between 0 and pi, the sine function. The values are between 0 and 1. If you take the reciprocal of those values, you get numbers bigger than 1, and it has to approach those asymptotes. So this portion of the graph looks like this. Similarly, over here at 3 pi over 2, the sine function is negative 1. The reciprocal of negative 1 is also negative 1. So this is going to be a point on the cosecant function. And all these values of sine between negative 1 and 0, the reciprocal of those values are numbers less than negative 1. And it, of course, approach the asymptote. So this portion, the cosecant graph, looks like this. So here's one cycle. Let's draw another one. Now let's look at some characteristics of the cosecant function. Let's look at the characteristics of the cosecant function. First of all, remember that when the sine of x is 0, it's undefined, so the domain is all real numbers except x equal n pi, where n is an integer. The range, so the domain, all real numbers except n pi. The range, we need to look at the y values. So let's look at these y values. Goes down to negative infinity, goes up to negative 1, and then it picks up at 1 and goes to infinity. So the range is this. The period is the same as the period for sine, which is 2 pi. And because it's undefined, it has infinitely many vertical asymptotes at x equal n pi, again, where n is an integer. You can see these on the graph. So asymptotes here I've shown at negative 2 pi, negative pi, 0, pi, and 2 pi. Now there's a couple other, for each cycle there's two important points for the cosecant. Let's look at this one first. This point is a relative maximum. This value of negative 1 is a relative max, because in this little neighborhood that is the highest y value. Where do they occur? Well, it occurs at 3 pi over 2, plus, of course, 2 pi times n, where n is in the integer, adding the period. Gets me to the next one. The maximum value is, of course, the y value, which is negative 1. Now let's look at this point. This point is where the relative min occurs. The x-coordinate where it occurs is at pi over 2. And, of course, to get to the next one, you add 2 pi, the period, times n, again, where n is an integer. The minimum value is 1. So those are two important points to know about. So let's see, let's underline them, the relative max and the relative min, and important what the y value is. And the function is odd, which means that the cosecant of negative x is negative cosecant of x, which means the graph is symmetric about the origin. You need to learn this graph and be able to graph it with showing the 2 points on each cycle and the asymptotes. Let's look at sketching functions of the form y equal a cosecant of bx minus c. Here my example is y equal negative 3 cosecant of x minus pi. To graph functions in this form, we're going to graph its reciprocal function, a sine bx minus c, that you should be very good at graphing. So our first step is going to be to sketch the graph of negative 3 sine of x minus pi. For this graph, we know the period is 2 pi because b is 1. We know there's a phase shift of pi to the right. And we know the amplitude is the absolute value of negative 3, which is 3. So let's sketch that graph lightly first. So the shift is pi. So remember, well, let me make some tick marks here. So let's see, pi and we need 3. Okay. So since the phase shift is pi, that means pi 0 is going to be a point for the sine. And then because a is negative, remember it's going to go down first. So at negative 3 pi over 2, it's down at negative 3, 0, up to 3, back down to 0. All right, so there's one cycle for the sine. Let's go ahead and sketch another one. So this is negative pi. So it's going to go up to 3, back to 0, down to negative 3, and back to 0. Okay, now we have two periods for the reciprocal function negative 3 sine of x minus pi. We want to get the graph of the cosecant. If the sine is 0, then we know we're going to have vertical asymptotes. So in this case, every time the sine is 0, here at negative pi, 0 pi, 2 pi, 3 pi, that's where your asymptotes are going to be. So we have an asymptote here, we have one on the y, we have one at pi, 2 pi, and 3 pi. Okay, so now that we know where the asymptotes are, we want to figure out the 2 points on each cycle. This point right here, this pi over 2, 3, we can see is a relative max for the sine function. That's going to be a relative min for the cosecant. And this point, which is, let's go ahead and label it. It was, let's see, 3 pi over 2. It's down at negative 3. That minimum point for the sine becomes a maximum point for the cosecant. So let's draw our graph. Okay, so we've got our points labeled. Next thing we want to know is what are the relative maximum points for the cosecant. Well, let's see where they are. This point is a relative maximum point, and this is a relative maximum point. What point is that? It occurs at negative pi over 2, negative 3, and then this one is at 3 pi over 2, oops, 3 pi over 2, negative 3. Okay, and those, for this 2 periods, those are the only 2 relative maximum points. Now, what are the relative minimum points? Well, for these 2 cycles, there are 2 relative minimum points. Let's go ahead and list those. This one is at pi over 2, 3. And this one is at 5 pi over 2, 3. So we have determined the easiest way to graph the cosecant is always to graph its reciprocal of sine, which you should be good at. And then once you get that, it's very easy. Every time the sine is 0, that's where your vertical asymptotes are. Get your label, find your 2 points for each cycle, and then sketch your graph. Remember, you approach the asymptotes. Once you have that, you can easily find your relative maximum and relative minimum points. You need to practice working these examples until you have mastered the skills and concepts involved. Let's take a look at the secant function y equals secant x. Recall that the secant function is the reciprocal of the cosine. So we're going to write this as 1 over the cosine of x, which means the secant will be undefined when the cosine is 0. And when is that? let's see, undefined. The cosine is 0 at odd multiples of pi over 2, which is a way of saying 2n plus 1 over 2 times pi, where n is an integer. What's going to happen for the secant is that's where the vertical asymptotes will be. First, let's do this. Let's sketch our basic function y equal cosine x that you should be very familiar with. So let's see, remember cosine, 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, 2 pi back up to 1. And then let's draw another period to the left. So negative pi over 2, this is 0, negative pi, negative 1, negative 3 pi, back up. Okay. All right, so here's our basic cosine function. So since the secant is the reciprocal of the cosine, we're going to be able to get some points. First of all, remember we said that wherever the cosine is 0, the secant will be undefined. That's where the vertical asymptotes will be. So I can see that there's going to be a vertical asymptote at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Next, this point here on the cosine, 0, 1, well, the reciprocal of 1 is 1, so this point will also be a point on the secant function. And all these values of cosine between 0 and 1, the reciprocal of those values are numbers bigger than 1, and it approaches the asymptotes. So this is what that portion of the graph looks like. Here we have a point for cosine, pi, negative 1. Well, the reciprocal of negative 1 is, of course, negative 1, so that will be a point on the secant. And all these values for the cosine between negative 1 and 0, the reciprocal of those values are numbers less than negative 1, and it approaches the vertical asymptotes as well. Here's one period for the secant. Let's draw another. Oh, I forgot this portion. Of course, reciprocal of 1 is 1, and then it approaches the asymptote. So here is 2 cycles for the secant function. You need to learn this graph and learn where the asymptotes are and those 2 points for each cycle. Let's look at characteristics of the secant function. First, the domain. Values of x are all real numbers except when x is equal to 2n plus 1 over 2 times pi, where n is an integer. That's another way of saying odd multiples of pi over 2 is not in the domain. The range would be the y values. If we look at the graph, we can see the y values go from negative infinity up to and including negative 1, and then it jumps up and goes from 1 to infinity. So that would be the range. The period is the same as the period for cosine, which is 2 pi. It has infinitely many vertical asymptotes, and they occur where it's undefined, which is x equals 2n plus 1 over 2 times pi. Again, same thing as odd multiples of pi over 2. So we can see our asymptotes are at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. The next one would be at 5 pi over 2. For each cycle for the secant function, there are 2 important points. One is where a relative max occurs, and it occurs at the x value pi. The next one would occur 2 pi away times n. Again, n is an integer. And the maximum value is negative 1. Again, in this region, this is the highest y coordinate. Here we have a relative minimum point. It occurs at x equal all multiples of 2 pi n. So one's at 0, the next one would be at 2 pi, negative 2 pi. Again, n is an integer. And the minimum value is 1. The function is even, same as the cosine, which means that the secant of negative x is secant of x. That's important. Let's underline relative max and relative min. And because it's even, that means that the graph is symmetric about the y-axis. It's important that you know how to graph the secant and know all where the asymptotes are and where those 2 points are.